today we have Julius who is our own. He's going to talk about a very exotic paper. And I also would like to tell you again that there's going to be coffee and tea available also after the seminar, some cookies too. And we also have another talk scheduled for the next week by Ruseckas from Ruseckas University, so that's going to be next week. And today we have Julius. Please go ahead.
Yeah, so today we will continue our tradition of journal club, and I will tell you about a recent paper published in Nature Communications, and also I will test a new Beamer theme, and let's see whether it looks okay or not. It uses some exotic fonts. Okay. So, here is the article. As I said, it is published in Nature Communications. And actually, it is a very strange article because when you think about it, it is very, very simple conceptually. It is about interference from three slits, like shown here. You know very well two-slit interference. It was made famous by Richard Feynman, and Feynman thought that interference from two slits shows almost all basic features of quantum mechanics. So the question is, what we will get new when we have not two slits, but three slits? Let us take a look first at two-slit interference. When we have two slits, for example, A and B, we can think that our path of propagation can go through slit A or through slit B. So the wave function is superposition of two wave functions. One wave function describes path through slit A, and another component describes path through slit B. And the whole wave function is superposition. And now when we want to calculate probability, we need to take a square of the absolute value, and we see that there is this interference term. But it is all well known. Now, what about three slits? Well, we can do in the same way. We have now three slits, A, B, and C. We have three components of wave function. Each of those components describes a path through one slit. For example, A describes a path through slit A. So we form a superposition of those three possibilities, take a square of the absolute value, and when we take a square, we get this. So, actually, such expression is valid for any number of slits when we write the function in this form. We see that here we get only interference of paths going through a pair of slits. For example, A and B or A and C. And the question is this expression right or not? Some people introduced so-called Sorkin parameter, that is deviation of interference pattern or probability from this expression. That is
this minus sign.
Well, because in this, you see, in this expression we have those probabilities, and if we write like this, we overcome them. Therefore, we need to subtract. So, Sorkin parameter describes deviation of interference pattern from the pattern calculated from this superposition principle. And naively, one can think that it should be zero. But actually, it is not true. It is not zero. And the reason it is not zero because we didn't take into account all possible paths when we write superposition in this form. Also, more exotic paths should contribute to to the wave function. One of those paths is shown here in red. That is, it goes through slit A, but doesn't reach the point of detection, goes back through slit B, and goes out through slit C. So, due to those loop trajectories, the sorting parameter is not zero, and when we have 3 or more slits, we actually cannot write the function in this simple form.
But with 2 slits, there are no such trajectories with loops?
Yeah. So you see, if you have only 2 slits, how do you form loop? You can go like this.
Yeah.
Yeah, but you still go from A.
But it's not the same. But go from A, return from B, and then one more time go from A.
Yeah, I agree.
But
no, it's not the same.
Phase factor.
What?
This looping would introduce a phase factor.
Yeah, but if you have the function that describes what goes through the slit A, well, it should include everything.
What does it mean, go through slit? I can, okay, go to the next slide. So the red trajectory, I can say that it's just go for slit C. Because it goes from, not directly, but it goes from slit C. And that's all.
I'm sorry, can I meet Alan?
Yeah.
So, can you go one slide back? So here, the psi A means that the particle enters through slit A and exits through slit A. And that is what distinguishes the 2 slit C from the 3 slit C.
Okay.
But I'm still thinking about what Victor has proposed. Generally, if you have a uniform space, maybe it doesn't matter that you make a loop, the phase goes away. But if you would have in homogeneity, maybe you would be able to detect that there are cases when you loop around.
That's right.
Yeah. Okay, but the contribution of such paths that goes into like loops, they have very small amplitude, and actually in real experimental situations, it is very hard to detect the difference between this, how to say, exact calculation and calculation using only this wave function. And the aim of the authors of that Nature Communications article is actually to detect the influence of such looped trajectories. The idea is like this. One needs somehow to enhance those trajectories. They say that loop trajectories are due to near-field components of wave function. And if we can control those near-field components, then maybe it is possible to increase the probability to go through a loop. And for increasing of near field, they propose to use surface plasma. As I remind you, surface plasmas are electromagnetic fields that are confined to the surface of metal, and they can extend over all 3 slits, and so they can make easier for the photon travel from one slit to another. The experimental setup looks like this. Another thing that the authors wanted to show that the results are valid for single photons also. And for obtaining single photons, they use 2 methods. One method is just to attenuate the laser, that is to take such a low intensity that we have almost 1 photon. Another way is shown here, using parametric down conversion. They have nonlinear crystals which convert the original laser light into, one photon converts to 2 photons, but with 2 times smaller frequency. Those 2 photons go through beam splitter. After one pass of the beam splitter goes to the detector here, and only when detector detects a signal, it sends a signal to CCD camera, and CCD camera only takes a picture when it obtains signal from this detector. And another photon goes here through the sample and into the camera. Parameters. So they used for those 3 slits, they use gold film. But if we want to have surface plasmon, we need to have metals. So they use gold film on a glass substrate. Dimensions are here. So the width of the slit is 200 nanometers. Length is 100 micrometers. That is the length is much larger than this. So this is done to reduce the problem to dimensional situation in order to make calculations easier. The distance between slits is 4.6 micrometers, and the width of the gold film is roughly 100 nanometers. And the wavelength used was 810 nanometers, that is infrared light. As you see, the width of the slit is smaller than wavelength. And now there can be 2 choices of polarization, basically. If the polarization of light is along the slit, then surface plasmons are not excited. If the polarization is in this direction, perpendicular to the slit, the probability to excite surface plasmons are large. And in this picture we see experimental data when a laser is focused only on one slit. On the left-hand side you see the picture when polarization is along the slit. So we have just broadening. But when we have polarization perpendicular to the slit, we see interference pattern, because now, although laser is focused only on one slit, but due to surface plasmons, light goes also from another slit, and those 2 paths interfere. You see interference pattern. Here is a numerical calculation of Poynting vector when laser is focused on one slit, on slit A. It's hard to see, but if you look at the arrows go like this. This is look from above. They go through slit A, then go parallel to the plate, then goes through the hole, B goes like this, and out of C. One numerical calculation confirm this picture that we have looped trajectory. Here is another picture, also from numerical calculation. Here is how interference pattern from 3 slits depends on the wavelength, and also 2 cases where polarization is along the slit, so surface plasmons are not excited, and here is shown the situation when surface plasmons are excited. So you see that there is a large difference between those 2 pictures. So at least numerical calculations show that in this case, when we have surface plasmons, those loop trajectories have large influence. And here is experimental data. On the picture on the left is this Sorkin parameter, and that is deviation of our interference pattern from calculation using only two-slit interference. Gray dots are in the case when polarization of light is along the slit, and blue dots are when polarization is perpendicular to the slit. And continuous lines are theoretical calculations. So we see that we detect significant difference from zero. That is, those loop trajectories in this case are really important. On next two pictures, we see dependence on the wavelength of the Sorkin parameter at the center, and also we have two different widths of the slit. Blue dots are for the width equal to 400 nanometers, gray triangles, then the width is 200 nanometers. In this picture, the polarization is perpendicular to the slit, that is, surface plasmons are involved, and here is parallel to the slit. The only thing that the authors of the paper didn't explain why they have this Sorkin parameter close to zero when the width of the slit is increased.
You know,
Yeah?
don't you find it very suspicious that by lucky chance they put the laser and the detector in such position so that the parameter is always negative in the first light of the blue spot? So we were so lucky that they only put the detector there. That's very suspicious.
You see, this parameter is calculated. To calculate this Sorkin parameter, you need to measure actually 6 things. You need to measure a pattern from one slit. You need to measure interference from two slits, and you need to measure interference from all 3 slits. And I didn't put the picture here, but you see this not a simple sample. This is, they have various arrangements of slits. In some places there is only 1 slit, 2 slits, and 3 slits, and they
Not the same.
number is slits are of the same size, but number of slits are different, and they measure all those probabilities, and after you measure probabilities, you can calculate the Sorkin parameter. It is not very straightforward.
Sure, but the theory says that it should be both negative and positive.
Yes.
But by lucky chance, they only hit the spot where it's negative. Very suspicious.
Yeah, good question. I don't know. Maybe they have some difficulties to measure positive parameters. At least the theoretical cards show that it can be positive and negative.
But I'm sorry, so in the next two pictures actually become positive sometimes. It's the same parameter, isn't it?
Yeah, it's the same parameter.
Yeah, but if you think, what's the chance of hitting only the negative spot in the first spot?
Maybe it is not governed by chance.
Yeah, but if the theory is correct, and the thing is correct because it's a fit, and now you repeat the experiment, and you pick 10 points, and all of them by lucky chances where the first parameter is negative, hunting from the just general point, something doesn't sound correct here. You see what I mean?
Well, for example, in the case of polarization, you have points above 0 and below 0, right? That's not false.
Yeah, but you see those points, they are measures, but theoretical prediction is this continuous line.
Actually, where is theoretical prediction for gray points on the first?
This line. So for gray points, it should be 0.
be like aligned to the slit also. Because let's say we have ABC slit, okay? And I put the position of the laser, let's say on A, okay? I measure when all ABC slits are open, then let's say I close A slit, okay? But the laser should be
position of the laser should not change.
So if the first figure where there's on each axis there's like it's the position
of the detector.
yes? So what is this position?
Well, when you have interference pattern, it goes from the slit in various angles. And you need to move your detector to measure in those different places.
Yes,
That was a detector position. In principle, you would be able to make a measurement in between the points, right? By making a plot and seeing that you have all negative.
Yes, it is actually strange that they choose such a detector position when theoretical prediction goes to negative or
That's why I say I think
two,
the
yes.
experiment is okay, theory is not complete. Something is not good with theory.
But their theory is just Maxwell equation. And also, well, not only Maxwell equation, but they need to have equations also for this metal.
It could be just a Gaussian, right?
It could be, yes, exactly. That's what I thought. It could be Gaussian.
Yeah, but still, they measure the circuit parameter,
Yeah,
not here.
measurements are okay.
So can we say that we find one slit is type that is polarizon for plasmon, we propagated another slit and
Yes. The picture is like this.
in this journal was it published?
And Nature Communications. Yeah, and this is a conclusion of that paper. Basically, they say what they said, that they detected contribution to the interference pattern of those loop trajectories. And they write that our work elucidates new properties of light that could be used to enrich protocols that really rely on interference effects such as quantum random walks and quantum simulators. Yeah, basically that is.
Is there anything quantum in this, or they have it?
Well, actually, you can calculate everything from Maxwell equation. So
But why did they use quantum?
I don't know. I think that they thought that maybe it is more impressive when they demonstrate this effect using a single photon. And the moral of the story is like this, that when you calculate probabilities using superposition principle, you should think that whether you forget some terms or not. Because for three slits, you see that when you write like this, you have forgotten some path.
So how do you need to write for quickly? How the formula?
So you need to add an additional term that gives you those loops.
So wouldn't it be more common sense, let's say, to couple two slits first and then the first in all like possible combinations, and the interference, not the interference, but the wave function would be written in this manner.
Actually, in this case, I think the easiest way to imagine is to use the Feynman method of trajectories and just some contribution of all possible trajectories.
Okay, what would be the result if they would measure using not metal or some other sample?
Well, if they did not use metal, they
There would not be loop that can be demonstrated what different without loop and with loop.
yeah, without using metal and without using those surface plasmons to enhance probability of transfer from this slit to that slit, contribution of those loops is very small and very hard to detect.
Yeah, I understand, but have they did measurement using only not metal?
They didn't write it, but I think they did not. But even with using metal, when they choose polarization along the slit so that plasmons are not excited, you see there is no interference pattern then, for example, when they shine onto one slit.
One slit or two slits?
One slit. Here they shine a laser only on one slit.
It means other slits are closed?
No, not closed, but the laser is tightly focused.
Okay.
It's focused only here.
Because when you showed the sample itself, you were discussing that there are cases when they just have one slit on the side, for example.
Yeah, but this figure is not for this case. This figure when they have three slits, but focus the laser only on one slit.
If I understand correctly, they only enhance two of the possible three trajectories, namely, like the trajectory. So the trajectory where the photon enters through B, goes back through A, and exits through C is actually not enhancing the shape, right?
No. Actually, as you see, there is infinite number of loop trajectories. But when you increase number of loops, the probability of those trajectories decreases.
Right, but what I'm saying is about a single loop trajectory. So I'm saying that there are three single loop trajectories, right? So that's one of them. There is another one which is the same where it enters through C,
Yes.
goes back through B, and exits through A.
And this is?
And the third one is when it enters through B,
Yes.
exits, well, it goes away through A back,
Yes.
and then through C out.
Yes, but this trajectory should have a smaller probability because, well, the probability to go from A to C, so the photon should travel larger distance, and probability will be decreased.
Okay, I have one question. Is this actually how to put loop, or is it only excitation of those plasma
Plasmons?
hormones, or the excitation which transfer to the next loop and emit? Can you say that actually loop or just excitation which later emits into the next loop?
Well, but this excitation is, well, plasmon is combination of electromagnetic field and charge fluctuation. So electromagnetic field travels on the surface of metal.
So if, for example, they would put their detector perpendicular to the list, they should observe something then?
What do you mean put detector perpendicular to the slit?
Like literally, I mean, if they have surface
Yeah,
platform
you can see
beside
it's not
it,
that-
they're on the whole surface. So if I put the detector like that, here's the slit, and here's the detector, perpendicular, literally perpendicular. So they wouldn't observe something then?
No, but the intensity map shows that the intensity decreases to the side, so it's actually then you don't need to have 90 degrees.
Yeah, actually intensity map you can
No,
hear.
not this one, on slide.
But here is also intensity map.
Okay. But on slide 15, that is
14.
no previous one. This one.
This is interference pattern.
So his question was now when we have white, would you see something if we have three slits open?
Here, three slits are open, but laser is focused on one slit.
So it means it does not go far away.
Yeah, those plasmons decay, as I understand.
I wonder if the photon loses any energy by exciting a plasma.
Well, how can the photon lose energy? You mean that its frequency should change?
Yes. Or your sample should heat. Of course, it would heat also because it's absorbed directly, but
What's the material?
Gold,
And what's the speed of the light?
infrared.
So it cannot, because it's decaying, well, it's the decaying field, because the energy of the plasma in gold is 3.2 or 3.4, that's not gold, so it cannot excite. It's just decaying evanescent field.
Yes, it's evanescent.
It's not enough energy. But if it's where it's provided, then it's a different story. It will lose energy.
And this was
So 2.8